Okay, let's look at a situation when you have moist air in contact with liquid water. Okay, so let's look at this situation. We have a closed system and we're going to have liquid water down here. So here's going to be some liquid water. Okay, and above that liquid water, you're going to have dry air and water vapor. Okay, now remember, dry air and water vapor, they're like a sponge. And this sponge is greedy. It wants to be saturated. What dry air and water vapor long to do is just be saturated. That's what it would like to do. And so at equilibrium, if we let this container just sit there, what would happen would be that the partial pressure of the water vapor would equal the saturation pressure of water at the temperature of the mixture. What would happen is that the dry air and water vapor would give energy to that liquid water to try to evaporate it until it got all of that water vapor into the mixture as it possibly can until it got to be saturation. Okay, that's what we want to do. So this is why when you let out, when you're washing dishes and you have, pots and pans out there and they have little beads of water on them, why they evaporate. Okay, the energy from the air comes over it. Air sees the water, says, "Hey, I want some of that water into the solution." It puts energy in, evaporates that air, evaporates that water, and brings it into that moist air. So that's what's going to happen anytime you have this situation happening. Okay. Now, the other idea we have to think about is something called dew point. Dew point. This is when condensation occurs. Okay. Now, when condensation occurs. So here we go. This is going to be our TV diagram. Okay, TV diagram, and here is going to be a line that's representing our partial pressure of our water vapor. Now let's say we're out here at point 1. Okay, point 1. And what we have for dew point is if we were to go down and lower temperature at a constant partial pressure until we reach this point here is going to be point 2. This is our dew point. Okay, this is when condensation occurs. So our current state is state 1. If we were to lower the temperature, remember, here's our temperature. If we were to lower our temperature at constant partial pressure until we reach state 2, that is our dew point. Okay. Now, when we get our dew point, what's going to happen is liquid water is going to come out of that solution. And when liquid water comes out of the solution, now the mass changes, and then there's going to have to be a recalibration. We're going to have to recalculate what the partial pressure of that water vapor is. We are always going to need to check what the dew point of our water is, or water vapor is, because that's an important point. We do not want to go below that dew point many times because things can happen. It will condense, it will change our problem. Okay, so if you have that in your problem, that state A is a vapor. Okay, we have to see if it crosses this boundary, which is the dew point. And if it is the dew point, what's going to happen is that some of this, let's say this, some of the substance of the mixture, I guess I say some. I'll just say some. Some stays as a vapor, and some turns to liquid H2O. Okay. Now it's not going to be like, it's not like it's going to flash and when it hits the vapor, the dew point, that everything just turns magically to water. That doesn't happen. Some of it goes away and it has to recalibrate those lines as it's going through and reaching equilibrium over and over and over again. Okay. The further we go down below that dew point, the speed that we go past that dew point, those are all things that are going to make how much water vapor are going to happen. Okay. So, you know, at night, when you have cool grass outside, you might see it starts to get dewy, you know, or your car might feel wet. What's happening? That car or or your grass is at the temperature that is the dew point, and so that air is coming by and it sees that grass blade and it starts to say, oh, I'm going to condense on that. Same thing would happen if you are in a very muggy climate and you have so the relative humidity is high, and you have a cold beverage, you bring it outside. That cold beverage is going to have a microclimate around it. That cup, that glass is going to have a microclimate. That aluminum can is going to have a microclimate where it's going to be colder than the surroundings. And so when air comes by it, it's going to say, oh, you're at the dew point of me. And so it's going to start condensing and it's going to attach to the side of that can. Okay. In the winter time, you come from the outside and you might have glasses on, and your glasses are going to be from the outside. It's going to be at, freezing, and maybe it's 20 degrees outside. When you come into a house, it's warm, moist air inside of there. The air is going to say, oh, the glasses are below the dew point. I'm going to start condensing on them, and then I'm going to have things fog up. So that dew point is very important. It's also important in industrial processes. When you have water, you have exhaust gases leaving a smokestack, you want to make sure that those exhaust gases are not going, that the water vapor is not going below its dew point, or you could have some acid rain type things that are going to be created. So that dew point is a very important piece of information to keep track of and understand. Okay. Now, as you get closer to the dew point, your relative humidity is going to go up. This is going back to that same discussion that we had before. So let's look here at a temperature. Let's look at our dew point, and let's look at our relative humidity. Okay. So if it's 90 degrees and the dew point is 80, our relative humidity is 67%. If it's 100 degrees and the dew point is 80, our relative humidity is 47%. And if it's 110 degrees and our dew point is 80, it's going to be 33%. Okay, so we're getting further and further away when we're looking at those, the relationship of how things are comparing there. Let's go back here to Google and let's type in, what is the dew point in Manhattan, Kansas? Okay, the dew point is 70 degrees right now. It's 70 right now. The temperature outside is 82. So maybe there's going to be some low-lying areas that are below, that are starting to reach really close to the dew point, and you start having maybe fog occur. So when you have a lot of fog in low-lying areas, that's because cold air is trapped in low-lying areas. Cool air sinks, and therefore it's going to be a place where that water vapor is going to come down here and start condensing and making into fog or a cloudy area. Okay, so those are all things that you've seen, that you understand, and now you understand the thermodynamics of that. Okay, now if it was 80 degrees in this example, if this was 80 degrees and the 80% dew point, okay, now you're going to have that things are starting to occur. Maybe you're going to have rain. Maybe you're going to have fog. Maybe something's going to be happening when your dew point and your temperature are the same. Okay, now how we feel inside of substance when we're dealing with this is something called the heat index. Okay, it may be 95 degrees outside, but if it's 95% relative humidity, I'm going to feel uncomfortable. And so there's something called the heat index that's talked about, and we actually feel much warmer than it is out there. Now, the world's record high dew point was 95 degrees. Think about that. 95 degrees was the dew point. Meant water was to start condensing out of the air at 95 degrees Fahrenheit. This has occurred in Duran, Saudi Arabia. Okay, the temperature that day was 108 degrees Fahrenheit. So our calculation of our heat index with a 95 degree Fahrenheit dew point and 108 degree Fahrenheit temperature, the heat index was 174. It felt like 174 that day. That's what it felt like. And the heat index takes into consideration clothing and blood flowing through your veins and everything like that. So I think in Canada they call it the humidex, things of that nature. So what we want to do as engineers is we want to make the temperature that it is outside what we're measuring actually feel like that. So at 80 degrees Fahrenheit and 45% relative humidity, it feels like 80 degrees. Okay, but here's the thing: at 110 degrees Fahrenheit and 17% relative humidity, it feels like 110 degrees Fahrenheit. So the hotter it is, the lower the relative humidity needs to be for it to feel like the actual temperature. Okay, so if you're in a house right now, the house is probably trying to keep with air conditioning about 75 degrees. We try to keep it about between 45 and 50 relative humidity because then it's going to feel like 75 degrees. It's not going to feel hotter or colder than that. Okay, if it was 75 degrees Fahrenheit and 100% relative humidity, it would feel about 5 degrees warmer. Okay, if it was 75 degrees Fahrenheit and 0% relative humidity, it would feel like about 70 degrees, about 5 degrees cooler, because your sweat would just be evaporating off of you really rapidly, trying to get into that air, trying to get into that mixture around you and cooling you down, so you would feel much cooler. All right. So those are the things we're going to have to deal with when we're talking about our goal here about the air conditioning process. How do we feel more comfortable? And that's where we're going to work on clothing and make sure we have this sweat wicking clothing and everything like that works into that. Okay, so there's a difference between relative humidity, which is this RH, and then the absolute humidity or the specific humidity or the humidity ratio that we're talking about there before. Okay, now that's where we're going to end today. We're going to continue this discussion in future lectures, and we're going to start talking about how do we set states, how do we look at properties, how do we do calculations with ideal gas mixtures of dry air and water vapor.